Hello everyone, welcome to lecture 3.4, which again is part of solving linear algebraic equations, where we're going to be focusing on the Gauss-Seidel and Gauss-Seidel with relaxation. Before we get into that, we're going to go into some of the things that we've looked at before, which is kind of finding when is our coefficient matrix A ill-conditioned. And if you recall, when we said ill-conditioned, we said that if we graphed it, it would be difficult to find the intercept, and also that it would be sensitive to round-off errors when we're using, Gaussian elimination and so on. So there are three direct methods to find if our coefficient matrix A is ill-conditioned, which is basically built off the coefficients from the set of linear algebraic equations. So the first one is we use scaled matrix A so that 1 is the largest number in each row. So scaling basically means that you multiply each row by a certain factor so that you get 1 as the largest number in each row. Then you find the inverse of A. If there are elements in the inverse that are several orders of magnitude larger or greater than 1, then that means your system is likely to be ill-conditioned. Another approach is if you multiply A by the inverse of A and it approximately gives you the identity matrix, then it's not ill-conditioned. And then if you take the inverse of matrix A and you get approximately matrix A, then also in this case it's not ill-conditioned, which is a good thing. But usually preference is given to a single number value that can be used to evaluate whether a coefficient matrix A is actually ill-conditioned or not, and that introduces the condition number, which depends on basically something called the norm of a certain matrix. So we're going to look at that briefly. So essentially the condition number or condition of matrix A is equal to the norm of A multiplied by the norm of the inverse of A. So if the condition number is greater than 1, then our system is ill-conditioned and round-off errors are likely to occur. So this number tells us or indicates the accuracy of vector x when solving a system of equations in ax equals b. Estimating which significant digits have rounding errors will basically depend on this equation here, where you take the log of the condition of matrix A and you get a value C. This value C is the last C significant digits of the solution could exhibit rounding errors. All right, so what are commonly used vector norms? In this case, for vectors, again, this is a vector, not a matrix. You can have the sum norm, which is basically the sum of all the absolute values in the vector, and that would be the sum norm. Or you could have the Euclidean norm, which is represented by L2 norm, and this is basically the square root of the sum of the squares of all of the components in the vector. So the general form is this form here, where you have, the norm of a vector x is the sum of basically the absolute value of all the components in our vector to the power of p, and all of this to the power of 1 over p. So again, that's just a general form. Another thing is just taking the maximum value in the vector, which is called L infinity norm, and this would be basically the norm using the method of the maximum norm. So basically, if I had a vector with 1, 2, 3, 4, 5, the maximum value is 5, so then the norm in this case would be 5. Now in terms of a matrix, so we have this matrix here. One of the most commonly used matrix norms is the maximum column sum norm, which is basically taking the sum of every column. So in this case, 3 plus 7 plus 6 gives us 16, 9 plus 2 plus 8 gives us 19, 5 plus 4 plus 1 gives us 10. So the maximum of these would be 19 in this case, and this would be basically the maximum column sum norm, or L1 norm. Another approach is taking the row sum norm, or it's called L infinity norm. So now in this case, we're adding 3 plus 9 plus 5, we get 17, 7 plus 2 plus 4, 13, and so on. And then the maximum number in this case is 17. So this would be our maximum row sum norm. Again, these would be values that you would use to calculate the condition number for a specific matrix that you're trying to basically determine if it's ill-conditioned or not. Another one is the spectral norm, which uses eigenvalues of the transpose of matrix A multiplied by A, and it takes the maximum eigenvalue in this case and then square roots it. So again, we're not going to go into much detail on eigenvalues in this course, so we don't really need to worry about that. Now we're going to move on to the Gauss-Seidel and Jacobi method, which are both numerical methods, and they're both iterative methods to solve a set of algebraic linear equations. In this case, we would basically have to follow this basic procedure. So we have algebraically solve each linear equation for xi. So basically, if you have 3 equations, each one you solve for a different variable, and we'll see that in an example. Then you start with an initial guess for all of the variables. So xi basically represents, if you have 3 variables, then it would be x1, x2, and x3. And then solve for each variable and repeat using the equations that you rearranged in this case. So use relative approximate error after each iteration to check if the error is within pre-specified tolerance like we did before. So why should we use these iterative methods? Basically, we control the round-off error that is basically seen in the elimination methods, the Gaussian elimination and LU decomposition. And in this case, in some cases, a close initial guess can be made to decrease the number of iterations using these methods. So we can use that Gaussian elimination or LU decomposition to find these initial guesses for our solution and then iterate using Gauss-Seidel or the Jacobi method, which we will see in a second. All right, so the Gauss-Seidel and Jacobi methods follow this kind of system where we have a set of linear equations. And what we're going to do is we're going to reshape each one of these equations to solve for different variables. So the first equation, I'm going to solve for x1. Second equation, I'll solve for x2. Third equation, I'll solve for x3, and so on. So it's similar in spirit to the fixed point iteration method, where we rearrange the equations and solve for x in this case. So here we have 3 equations. So in the first equation for a 3 by 3, we're going to solve for x1. So we would get x1 equals b1 minus a12 x2 minus a13 x3 divided by a11, which is the coefficient of x1. In the same fashion, for the second equation, we solve for x2. And then in the third equation, we solve for x3. So we get these 3 equations where each one is, basically solving for one of the unknown variables that we want to solve for. Then in this case, now we can start the solution process by choosing guesses for all of the values or the variables. So we have x1, x2, and x3. So we can have initial guesses for those. And then using these initial guesses, one of the most simplest way to basically have an initial guess is assume that all of these variables are equal to 0. Then these zeros can be substituted into these equations and basically solve for basically the first iteration of x1, x2, and x3, and so on. So the Jacobi method calculates x1, x2, and x3 using old values of x1, x2, x3. So, basically the second iteration depends on the first iteration's values from x1, x2, x3. The Gauss-Seidel, on the other hand, every time we update one of those variables, we're going to use them in the next calculation. So for example, if I calculate a new x1 using the initial guess, then I'm going to update my x1 when I'm calculating x2. So in the equation for x2, I don't plug in the initial guess for x1. I use that new value that I just calculated. And then when I'm calculating x3, I use the updated x2 to evaluate x3. And then this procedure is basically repeated until convergence criterion is satisfied. So that is the main difference between these two methods. And then obviously for convergence, we're going to check what is the current estimate for a variable x compared to the previous estimate divided by the current estimate times 100. And we want to check that this is lower than some certain tolerance. And in this case, the I is basically representing all the values of, if we have 3 values, then I is 1, 2, 3. If I have, and J here is basically the iteration. So J would be the current or present iteration, while J minus 1, which is what we see here, is the previous iteration. All right, so another kind of picture here or figure that shows us the difference between Jacobi and Gauss-Seidel method. In the Jacobi, we do the calculations for all of x1, x2, and x3. Then we plug those new values into the second iteration calculations. While in the Gauss-Seidel, every time I find a variable, I'm going to plug it in to the next equation to update x2 using the updated x1. In this case, x3 would be the initial guess. And then when I'm trying to find x3, I'm going to plug in the updated x1 and the updated x2 to find x3, and then we just continue that way until we converge. All right, so let's do a quick example here. Let's imagine we have two equations. We have x1 plus x2 equals 2, and x1 plus 2x2 equals 3. We need to rearrange these equations to solve for, in the first equation, x1, as we see here. And then in the second equation, I want to solve for x2, as we see here. We set initial guesses. In this case, we can set them as zeros. And then we start by iterating. So in the first iteration, I'm going to use this equation to solve for a new guess or a new estimate for x1 using my initial guesses that we see here. So in this case, I'm going to write 2 minus x2. In this case, the initial guess for x2 is 0. So I'm going to plug in 2 minus 0 will give me 2. So now this is my updated value for x1. So when I'm calculating x2 and I need x1, I'm going to plug in this updated value. I'm not going to plug in this old value when I'm following the Gauss-Seidel method. So in this case, it would be 3 minus 2, which we got here, divided by 2 equals half. We check the relative error, percent relative error. As you can see here for our first kind of x1 value here, we get 2 minus 0 divided by 2 is 100% error. And then half minus 0, which is the initial guess, divided by half times 100% gives us 100%. Second iteration, now we plug in the updated value for x2, which is half, into this equation, right? So we have 2 minus half will give us 3 over 2. And then for x2, we plug in this updated x1. So we have 3 minus 3 over 2 divided by 2 equals 3 over 4. And again, we check the percent relative error. We can see here that it's decreasing. So we have 33.33% for x1. And for x2, we have the same value. Then you repeat this, the third iteration, we get 5 over 4 and 7 over 8. Fourth iteration, we get 9 over 8 and 15 over 6. So I encourage you to try these out to make sure you understand how the Gauss-Seidel method is basically done. And this is basically the basic Gauss-Seidel method, not the Gauss-Seidel with relaxation. So convergence criterion for Gauss-Seidel method: if basically you have a coefficient matrix where the diagonal values are greater than the sum of all the other values in a specific row, then this is basically meaning that you have a diagonally dominant elements within your coefficient matrix A, then for sure when you're using the Gauss-Seidel method, it will converge. All right, so now we move on to when we want to use relaxation with the Gauss-Seidel method. The main factor here is lambda, where we're following this equation here, essentially. So our new estimate of the variable x will be equal to lambda times the new estimate plus 1 minus lambda times the old estimate or the initial guess. So this lambda value, if it's between 0 and 1, then it's under relaxation. If it's equal to 1, then no relaxation. Basically, this would be 0 and this would be 1. So we're just taking the new value as the new value and not doing any relaxation. And then if I plug in a value between 1 and 2, right, so a value greater than 1 and less than 2 or equal to 2, then I am over relaxing. So for example, in here, if I plug in 2, I'm going to multiply this new value by 2 plus 1 minus 2. In this case, this would be a negative 1. So a negative 1 times the old value. And basically, we are trying to jump ahead to find the value for x in a faster kind of procedure. So one approach is to use this as a constant value and just do all the math. Another approach is probably to use a variable lambda value. So initially, when you're starting with the initial guesses of zeros, you basically over-relax, but as you move on with the iterations, maybe you want to go into under-relaxation so you don't miss basically the solution and jump over it. So again, if you write a code, you can manipulate this lambda value if you're following the relaxation method. All right, so let's do an example with relaxation. Taking the same example as we had before, these two equations, we rearrange x1 and x2, so from these two equations, and we have our initial guesses of x1 equals 0 and x2 equals 0. In this case, we're going to use over relaxation where lambda is equal to 1.2. So in the first iteration, we have x1 equals to 2 minus x2, so 2 minus 0, right? So 2 minus the initial guess of x2, which is 0. We get a value of 2. Now I take this value and I plug it into this equation with the 0 and the 1.2. So what we get is 1.2 times 2, which is 2.4, plus negative 0.2, which is what? 1 minus 1.2. That's how we get the negative 0.2, multiplied by the initial guess, which is, in this case, 0. So then we end up with 2.4 as our estimate for the solution for x1 instead of 2. So you can see how we're over-relaxing, meaning we're jumping ahead. If we were under-relaxing, then we would get a value basically between 0 and 2. And if we're no relaxation at all, then we would just use the value of 2 as is. So again, in this case, we're over-relaxing, and we would follow this equation here. Then we would go to solving for x2. And in this case, we would use the updated x1, which includes relaxation. So 3 minus 2.4, which we got from here, divided by 2 will give us 0.3. Now we apply this equation here of over-relaxation on this value, and we end up with a value of 0.36. So again, we jumped ahead using this over-relaxation equation. And then second iteration, 2 minus 0.36, which is what we got here, and we get 1.64. And then again, we apply the relaxation equation. We get 1.4880 in this case. So in this case, we did not jump ahead. We moved a bit backward, but we went from 2.4 to 1.64. So we are jumping, but in the negative direction, right? So instead of from 2.4 to 1.64, then we're jumping even further in the negative direction, which is 1.4880. Again, for x2, we apply the same thing, 3 minus the updated x1, 1.4880. We get this value, and then we do the over relaxation. And when we're going from 0.36 to 0.756, we are increasing in values. So then the over relaxation would jump ahead further, as we can see here. All right, so you continue with these iterations until you converge, as we see here. All right, so now we're going to look at nonlinear systems, right? And this is basically, you could use the Gauss-Seidel method with nonlinear equations. And again, this is called successive substitution. So everything we did before, you continue. And again, it's the same strategy as the fixed point iteration that we've seen before. Another approach is to use the Newton-Raphson method, which is derived from the first order Taylor series, which is set to 0 as we see here. So we can see f of xi plus 1 is equal to f of xi plus the slope times the step size equal to 0. So for a set of nonlinear equations, we can use also this type of approach, but the Taylor series would be a Taylor series which is for more than one variable. So how does that look like? We'll look at that in a second, but essentially, if I have a set of nonlinear equations, such as what we see here, function 1, we set it to 0, function 2, we set it to 0, and so on. So as an example, if I have x squared plus xy equals to 10, I'm going to move this 10 to this side so that it would equal 0, and this would be my first function, f1, or we can call it this variable u. Our second function here, or second basically nonlinear equation, we do the same thing. We rearrange it so that it's equal to 0, and we call it a variable either f2 or a variable here, in this case, v. We take this function, and then we apply the Taylor series, but this is the Taylor series for more than one variable. So here ui plus 1, which is from the first equation, is equal to ui plus the derivative of ui in terms of x, plus the step size, or times the step size, plus the derivative of ui in terms of y times the step size in y, equal to 0. Same thing here for the second equation, but instead of u, we have v in this case in the derivative that we see here. So what we see here is basically this equation rearranged. So what we have is the derivative of ui by x, right, multiplied by xi plus 1. So this is xi plus 1, plus derivative of u in terms of y times yi plus 1. So that's what we see here, these two terms. Then on this side, we have everything that's remaining. So this ui is moved to this side, so it's a negative ui. And then this multiplied by this is a negative on this side, but if I move it to the other side, it's a positive, as we see here. And then the change in ui, or the partial derivative of ui by y times negative ui is negative on this side, but if I move it to the other side, it becomes a positive. So the same thing is applied to this part of the second equation, where we're rearranging to get these kind of partial derivatives multiplied by the future values of xi plus 1 and yi plus 1, which are basically, in every iteration, would be the next estimate of what are x and what is y that would solve the set of nonlinear equations. So this in matrix form looks like this. So this exact thing here is basically transformed into matrix form. We can see here ui, the partial derivative of ui by x, right, multiplied by xi plus 1, and then this derivative, partial derivative, multiplied by yi plus 1, and so on. So, and then this negative ui and negative vi are here, plus another partial derivative, basically matrix, multiplied by the initial guesses, or the previous iterations, values of xi and yi. All right, so since we know everything in here, we know basically the derivative at the initial values. We know the values of the function using the initial guesses. The only thing that's unknown is xi plus 1 and yi plus 1. So you would want to rearrange this equation to solve for xi plus 1 and yi plus 1. In this slide, essentially what we have is the general representation of the solution when you have many equations. So the format is you have the Jacobi matrix, which is all the partial derivatives. So if you can see here for the first function, we would do the first function partial derivative in terms of xi, right? Second column is the function in terms of x2. Third column is in terms of x3. And then, last column is in terms of xn. Second row of the Jacobi is the second function in terms of x1, then x2, then x3, as we see here, and so on. Then we have a vector matrix, or a vector xi plus 1, and this would be basically a vector for each one of these variables in there. And then we have our negative value of the functions, right? So these are the functions. If you remember from the last slide, we had negative u and negative v. So this would be what's that there. And then again, we have the Jacobi matrix, and then we have our vector of initial guesses, which is xi here. All right, so again, in general form, the Jacobi is this, xi plus 1 is what we see here, and then this would be our function values using the initial guesses, and then this would be again the Jacobi, and this would be our initial guesses vector xi. So how do we solve this? Well, basically, this is how it looked like in the previous slide. We rearrange, so we have the Jacobi in here twice. So what we do is we factor it out. We have xi plus 1 minus xi, so that's what we did here, equal to negative of the function, what we see here. And then what we do is we take the inverse of the Jacobi. So we're going to move this and multiply it by the negative value of the function at the initial guesses. And then we just move over this xi to this side, as we see here. So it would be a positive xi. So this is basically the vector matrix with the initial guesses. And this would be our future estimates of the variables in the set of nonlinear equations. All right, so let's look at a quick example here. We have these two equations. All right, we're going to rearrange them to solve for and make them equal to 0. So now we have function 1 here. This is the first function. Function 2, what we see here, and they're both set to equal to 0. Now, in terms of the Jacobi matrix, right? So this is the format that we're trying to solve for. So we need the Jacobi matrix, and we need the inverse of that. We need a vector of all of the values of the function at the initial guesses, and we need a vector of the initial guesses. So the Jacobi matrix, we have the first function, partial derivative in terms of x1. So this becomes, in terms of x1, 2x1 plus, again, in terms of x1, this would be x2. So this is what we have here in the first part of this Jacobi matrix. The second column right here in the first row, we take the first equation again, we take the partial derivative in terms of x2, and in this case, all there is in terms of x2 is this x1. So that is what is remaining there. And then we apply the same thing with the second equation, where we take the derivative, partial derivative in terms of x2, and then here would be, in terms of x1 first. So that would be 3x2 squared for the first part, and then for the second part, we take the partial derivative in terms of x2. So then we would get 1 plus 2 times 3, which is 6, times x1 times x2, and this becomes basically a 0 when we take the partial derivative because there are no variables here. So that's Jacobi. Our initial guesses in this case, let's set them to 1.5 and 3.5. So what we do is we plug those in to the Jacobi matrix. So we get 6.5, 1.5, right? So 2 times 1.5 plus 3.5 is 6.5. You do the math for the rest of those, and then you find the inverse of this Jacobi matrix using you could use MATLAB, or you could do the method that we did with the LU decomposition. All right, so that's the value for the inverse. And then for the function f of x, basically what we do is we plug in 1.5 for x1 and 3.5 for x2. Whatever value we get, we plug it into here. So that's the negative 2.5. And then we do the same thing with the second function. We get 1.65. And then what we do is basically try to solve for xi plus 1. In this case, in terms of the iterations, j would be equal to 1. And then in the initial guesses, j is equal to 0. So this vector of initial guesses, 1.5 and 3.5, minus the Jacobi multiplied by the f vector matrix, which is basically functions at the initial guesses, we will get basically the estimate of the solution for x1 and x2 in this nonlinear equation as 2.036 and 2.8439. And basically, we continue this until we converge. You could also do this for, larger systems. So here we can see a 3x3 system. Again, you rearrange, you find the Jacobi matrix, and so on, and you continue. To solve this solution using this basically 3x3 system, and as you can see, these initial guesses are 1s. You plug in these 1s into these equations. So here you have 1 squared plus 1 squared plus 1 squared minus 1 gives us a 2. And you do the math for the rest of those. And then Jacobi, you plug in the values of 1s in here. You get this, you get the inverse of this matrix. And then you can solve for the first iteration of the unknown variables, x1, x2, and x3, as we see here, just like in the last example. But in this case, we have a 3x3 system. All right, and then you continue. So that was the first iteration in the last slide. Then you do the second iteration, and then the third iteration, and so on. All right, so if you have any questions, please email me. Other than that, we have a practice problem here. So this is going to be essentially a system, a nonlinear system, where you have two variables, x and y, with initial guesses of 1.2, and you want to rearrange basically the equations. So this would be equation 1, and this would be equation 2 rearranged, and solve using Gauss-Seidel method. And here what I have is the initial guesses of 1.2 and 1.2 for x and y. And in the first iteration, you should get these values. Second iteration, you should get these values. Third iteration, you should get these values, and so on. So practice this problem on your own and try to apply the Gauss-Seidel method to get these variables. All right, another thing that you could practice is add a relaxation to this system. I don't have the solution with relaxation, but you could also try it out to make sure you understand how the relaxation is applied in this case. All right, so that ends basically Unit 3. So in the next lecture, we are going to start Unit 4. Thank you.